So here we talk about the cyclotrons. So here the figure is a top view of the region of the cyclotron. So this is a cyclotron, this is an oscillator, so in which the particle, say proton, circulates. And then the two halo D-shaped objects are made of sheet copper. So this looks like a full circle, but actually we try to split it apart a little bit. So this is two half D shape, and then S is the source. So these as they are called, are part of the electrical oscillator that alternate the electric potential difference across the gap between the D's. So we try to put some E field between this gap, and then the B field is uniformly distributed over this whole disk. Yeah. And then the point here is that suppose we try to alternate the direction of the E field with a specific frequency, then we will try to accelerate the velocity, accelerate the particle gradually. Yeah. And we just go to here to explain the idea of this synchrotron first. Yeah. So yeah, the idea is like, suppose we have a gap in between. And then we assume the source is here, and then it try to emit a particle, just say a proton, which is a positive charge. A proton is a positive charge to the left side, and then there are B field pointing out of the page. I just draw some B field pointing out of the page. So this is a cross field, and then this particle will be in a circular motion like this. Maybe I draw it smaller. Okay. So this is the initial speed, and then it will turn around by the B field, as much as it has a Lorentz force. There is a B field in this region. So there will be a circular motion for the charged particle up to this point. And here we assume the E field. Here we assume the E field is pointing to the right side, And in that case, for this gap, there is no B field, so there will be no magnetic force. So the charged particle will go this way. Okay, so next we try to make it like, yeah. So during this region, this is an E field, so it will accelerate the particle from this point to that point. So this is V1, and then V2 is bigger. So it makes V2 is bigger than V1. And as we mentioned, for this circular motion, this radius is perpendicular to the velocity. R is proportional to the V. So in this case, V2 is larger, so the radius will also be larger. The radius will also be larger because V2 is larger. So up to here, V2. And at this moment, we try to make the E field in between to be pointing to the left side. And in that case, the particle will be accelerated by the E field pointing to the left side. So it becomes a V3 at this point, and V3 also is bigger than V2. So V3 is larger, so the radius here is also larger. So it becomes like this, go to here, and then at this moment, we try to make the E field point to the left, point to the right side again. Point to the right side again. So in that case, this is V3, and then the E field point to the right side, and then it becomes V4 here. So on and so forth. So it is like it has a shape like this. The radius becomes larger and larger. Although this is a semicircle, this is another semicircle with a larger radius, and then another semicircle with a larger radius, so on and so forth. So up to there, and then we can try to shoot this particle out. So the velocity of this particle accelerator depends on the radius and also the magnetic field because you can imagine, given a fixed particles, for example, here we talk about the proton, so m is a fixed value, and for proton, q is also a fixed value. So these two term is fixed. So here we have r is proportional to v over b, proportional to v over b. So in this case, if we want to make v to be larger, we should provide a larger b. Or we can imagine v is proportional to rb. So we can either increase the b field given in this region, or we can make this to be larger, which is the radius. So to get a higher velocity particle. So in this case, as much as you know, we need to generate B field, we need energy. So we need to generate the uniform B field in a large region. So it is difficult. So for this cyclotron, the energy is limited to 50 mega eV, which is not really large. Okay, but yeah, the idea is easier to understand. And of course, just mention for this part from V1 to V3, V3 to V4, the E field should be pointing to the right side, and from E2 to V3, V4 to V5, something like so on and so forth, the E field should be pointing to the left side. So we need to alternate the E field with a fixed frequency, so that it is not the case that when the particle move to here, the E field still point to the left side, then it will decelerate. So we need to control the frequency very correctly, and this frequency is nothing but this f oscillate equals qb over 2 pi m. And if you still remember, just last hour, we know the period is 2 pi m over qb, which is the reciprocal of this oscillating frequency, because ft should be 1, f is 1 over t. Yeah. So actually, we need to alternate the frequency, the E field direction with this frequency to make the cyclotron operate properly. Okay, so it has an energy limitation up to 50 mega eV. So we have another one called the synchrotron 同步加速器同步加速器This is called 同步加速器 This is called 回旋加速器回旋加速器 Okay, so yeah, for the synchrotron, we will not go deep into the mechanism, but the point here is that we do not try to because the point here is for the synchrotron, the limitation is that we need to provide a uniform B field over the whole area. So for the synchrotron, we try to make it like a ring, so that we only provide B field uniformly inside this ring, so that the area should be smaller and we can provide a larger B field inside this synchrotron. This is the point here. So the magnitude B and the oscillating frequency, instead of having a fixed value as conventional synchrotron, are made to vary with the time during the accelerating synchrotron, which is done properly. So we try to make the control more complicated, and that we only need a smaller area to, actually the area is not small in. The radius should still be large, but the cross-section area is smaller, so that we can make a larger B field inside this region. And in this case, the control of the E field should be more complicated to maintain the particle is accelerate inside this ring. Otherwise, it may collapse with the wall and then it will decelerate. Okay, so in that case, the frequency of the circulating proton remain in step with the oscillator at all time and blah blah blah, and yeah. The circular path, however, still must be large if high energy are to be achieved. So for this synchrotron, you can check the so-called the proton synchrotron. If you're interested, you can check it on the Wikipedia. It says that the beam is then injected into the proton synchrotron booster, which means that we try to accelerate the particle first to some value up to 1.4 GeV, and then it can inject to the proton synchrotron itself, and then this proton synchrotron can push the proton from 1.4 GeV to 25 GeV. So this 25 GeV is of course much larger than this, or 50 MeV. Okay, so let's see a example about the synchrotron. Not the synchrotron, the cyclotron. So suppose a cyclotron is operated at an oscillating frequency of 12 MHz and has a D radius R equal to 53 centimeter, which is not so large. But for this one, it can be up to kilometer level. So which is the magnitude of the magnetic need to be deuteron, which means it has one proton and one neutron to be accelerated in the cyclotron. The deuteron mass is m, like this. Okay, so it asks what is the magnitude of the B field. What is the magnitude of the B field? So we can simply make use of B equals 2 pi m f oscillate over Q, which means we make use of this equation, and then we move all the things to the left side except the B. So we have the expression like this, and then we can plug in the numbers. 2 pi times m is 3.34 times 10 to minus 27, and then times 12 megahertz, 12 times 10 to the 6th power over Q, one proton and one neutron. Neutron is electrically neutral, so it is 1.6 times 10 to minus 19. Okay, so this number is 1.57 Tesla. 1.57 Tesla. Okay, so this is the first one, and then the second one. What is the resulting kinetic energy of the deuteron? So we can try to find V equals R Q B M, because we have R equals mv over qb like this. So we can just move over the things. So we have a V equals RQB over M. Yeah. So we can plug in the values. R is 53 centimeter, 0.05 meter, times Q is 1.6 times 10 to minus 19 times 1.57, and then over 3.34 times 10 to minus 27. So this number is 3.99 times 10 to the 7th power meter per second. This is the velocity, and then the kinetic energy is half of mv squared. So it is half times 3.34 times 10 to minus 27, and then times 3.99 times 10 to the 7th power quantity squared. And this number is 2.7 times 10 to minus 12 joule. And usually for the particle physics, they usually use the EV, so we divide this number by 1.6 times 10 to minus 19 to make it 17 mega EV. 17 mega EV. So this one matches the value here. So it says for the cyclotron, the energy could be less than 50 mega EV. So suppose this number will make sense. So the radius is 53 centimeter with a 12 megahertz quark, and then the particle can be as fast as 17 mega EV. Okay, so before we move on, let me try to explain why the physician need the particle accelerator. And yeah, the point is that the physician tried to find the fundamental particles, fundamental particle. Let me see, 21. As I mentioned in chapter 21, I showed the standard model for the elementary particles. Yeah, of course, for high school chemistry, you only know the proton, the neutron, and electron. But yeah, actually, the physician tried to find whether there exists any more fundamental or more elementary particles in the universe. So they try to break this proton or the neutron into even smaller particles, just like you play the Legos. There are some elementary blocks. So they try to, the idea to break it is to accelerate and then make them to collide with each other. And then if the energy is high enough, then they may be possible to collide into smaller pieces. So you can just see here, actually the proton and neutron are construct with the up-down quad, and then you can see this is the mass. It does not use the kg for the unit, rather than that it use mega eV over c squared, because you should you should know E equals mc squared. E equals mc squared. So this is the energy if all the mass is transferred to the energy. So in that case, m is E over c squared. C is the speed of light. C is the speed of light. This is speed of light. Speed of light. Speed of light. So this is the energy. So actually, you can see for the first generation, for the quarks, it is as much as several mega EVs. But here, up to around 100 mega EV or up to 1 giga EV. So we need larger and larger energy, or make it we have larger and larger energy to really find the existence of this quark. So maybe there will be the fourth generation, but yeah, it needs even larger and larger energy to really find whether does it exist. So the point here for the particle accelerator is like this for this particle physics research. And just go back to here. Okay, so here we talk about the magnetic force on a current carrying wire. So I will also consider it to be the Lorentz force, which is QVB. FB equals QV cross B. So actually, it looks very similar. So let's see what is talked about. So here it says a straight wire carrying current I in a uniform magnetic field experience a sine wave force. This one. So comparing this one and this one, you can see we have a scalar in the front. Here we have a current. And then for the Lorentz force itself, we have a charge, and then we have a L cross B, we have V cross B here. So let me find whether there are some relationship between them. So it actually says that suppose this is a wire, and then we have B field perpendicular to it. For example, this case, the B field is pointing out of the page. If there is no current, there will be no force acting on it. And now, if there are current going from bottom to top, then there will be a force acting on it to the right side, FB to the right side. And if the current is going from top to bottom, then the FB is pointing to the left side. So let's see why it's like this. So maybe you just see. If we believe this to be correct, then how do we use it? Current is current. This is current. So going from bottom to top. So this L is the length vector. The length vector, of course, the magnitude is the length of this wire, and then the direction of this length vector is the same as the current, the same as the conventional current. So in this case, L is pointing upwards. Okay, so if we make use of it, L cross B, L pointing upward, B pointing out of the page. So L cross B is pointing to the right side. So which match this match this case. And for the part C, current going from top to bottom, which means that in this case we consider L pointing downward. Okay, so if we have L cross B, L pointing downward, and then B pointing out of the page. So FB point to the left side. FB point to the left side. So which also match these cases. So yeah, so this is the magnetic force acting on a current carrying wire. So if we have a wire and then we have current going through it, if there are no B field, then there will be no force. If there are B field but no current, then there will be no force either. However, if we have current going through a wire and also B field perpendicular to the current direction, then there will be force acting on this wire. Okay, so let me tell you the relationship between the Lorentz force and actually this one. So maybe I will call another version. So this is so I also consider this is a type of the Lorentz force. So you can simply imagine if we have Q, and then we have V cross B. So V cross B, V is something like V is dl dt. Okay, so V is just take the derivative. Take the derivative of the displacement with respect to the time. So you can regard it as dl dt times B. Yeah. And then Q times it. So actually we can just put this one to the front, and then we will have dq dt times L cross B, like this. So this one become I, So actually I will also consider this is a kind of Lorentz force, because the point here is that if you have current going from bottom to top, which means that there is electron going from top to bottom. So the V is pointing to the bottom, and V cross B is pointing to the left side, and it is a negative charge, so it points to the right side. So using the Lorentz force, you can also get the same expression, get the same explanation for this phenomenon. So I will also consider this is the Lorentz force. Okay, so here we talk about dFB equals I dl cross B. So we just make it dF and then dl on both sides, which means that if the current is not a straight wire, if the wire is not straight or the field is not uniform, then we can just separate the wire into many small segments, and then for each segment there will be a small differential force acting on it, and then we can calculate the whole force by integrating the whole wire. Then we get the whole force acting on the wire. Okay, so yeah. So let's see this sample problem. Okay, so here a straight wire, horizontal length of a copper wire has a current I. Yeah, going out of the page, because L is going out of the page, so we also can see that I is going out of the page through it. What are the magnitude and direction of the minimum magnetic field B need to suspend the wire? That is to balance the gravitational force on it. The linear density of the wire is 46.6 gram per meter. Okay, so here we have a horizontal wire there. Of course, it will be so the gravitational force will act on this wire. So we have mg pointing downward. So this is the density. This is the density per length, the linear density. So we multiply this one by the length, then it will be the mass of this wire multiplied by the G 9.8 meter per second square will be the gravitational force acting on this wire. And now we need to provide some magnetic field. And as much as it has some current going through it. So if the direction of the B field is correct, then it asks you to have the magnetic force cancels the gravitational force. So here L pointing out of the page, if B is pointing to the right side, then L cross B is pointing upward. So we know that the B should be pointed to the right side, and if B is large enough, then FB will be equal to mg. So we try to make it like FB equals mg. So FB is in vector form, it is F equals I times L cross B. So if they are perpendicular to each other, so FB is nothing but ILB. So we have ILB equals mg. So we would like to find B. So we move IL to the right side. We have a mg over IL. So the mass is 46.6. Actually, m over L is 46.6. And then, or maybe I can write it out, which is like m over L, which is actually this linear density, and then we still have a G over I like this. So we have 46.6. This is gram per meter, so we need to convert it back to the SI unit kilogram. So times 10 to minus third power, and then times 9.8 meter per second square, and then over 28 ampere. So yeah, so this number is 1.6 times 10 to minus second power Tesla. So as I mentioned before, the electromagnetic force is much stronger than the gravitational force. So we only need this small B field, yeah, to balance the gravitational force. Okay, so here we talk about the top on the current loop. Yeah, the top on a current loop. So here, suppose we have a current loop like this. The current is going counterclockwise, and then yeah, this is an axis. So that this current loop can rotate along this axis. And then we provide a magnetic field uniformly pointing to the right side. So this is the north pole, this is the south pole, the B field pointing from the left to right. So as shown in the figure, right, the net force on the loop is the vector sum of the force acting on its four sides. So this is a cross section of this figure. So you can see this is the axis, and then this is the loop. And yeah, and suppose this is this is counterclockwise, and then this is one of the line. The I is going from top left to bottom right, which is actually this one, going from here to here, And then actually the current here is going out of the page, going from this point to this point. So this is going out. This is going out. This is going in. This is going in. So, and here we have the B field pointing to the right side. So now we can try to consider what is the force acting on it. So, yeah. Yeah. So this is pointing out of the page. This is pointing out of the page. L is pointing out of the page. B is pointing to the right side. So for this one, which means this point, L cross B, L is pointing out of the page. L pointing out of the page, B pointing to the right side. L cross B is pointing upward. So F1 is pointing upward, acting on this Y, And similarly for this one, L is pointing into the page. L is pointing into the page for this one, which is this one. L is this one. So L is pointing into the page. L cross B is pointing into the page, cross to the B field, and then pointing downward. So we have F3 pointing downward. And then how about F2 and F4? This one, L is in this direction, and then yeah, there will be no force acting on it along this axis, because even though you have some current going, for example, in this way, L pointing from top left to the bottom right and then cross B, it will just be a normal force, so it will not make this loop rotating along this axis. And similar for that one, L cross B, so somehow like that. So this is just a normal force acting on this loop. Okay. So there are only two forces acting on this loop to make this loop rotating. So this one pointing to the upward, this one pointing to the downward. So it will make this loop rotating clockwise. And yeah, and here the torque, suppose it is rotating, so the torque is given by this equation, N times I A B sine theta, or we can actually write it in the vector form, equals mu cross B. So actually NIA will be the mu, which is called the magnetic dipole moment. B is actually this B. So you see this is a sine theta, which means that we have a cross product, and then the theta is the angle between the mu and the B, and this is the loop. So we have the cross section area to be A. And then we can also consider the direction of this area to be something like this. This is the direction of mu, or the direction of A, following the right hand rule, because here the current is going counterclockwise. So you can use your finger, follow the direction, and then your thumb is pointing this way. So yeah, you can still use the right hand rule to determine the direction of this magnetic dipole moment on the area vector. N is the number of turn, And in this one, 2 or 3 chapters, you need to distinguish about capital N and small n. We usually use capital N for number of turns, and then the small n for the number of turns per unit length, something like that. And of course here we only have a number of turns here. So n is the number of turn. So this is like mu. The magnetic dipole moment is the n times A is the current, and then A, NIA. So we have a mu cross B to be NIAB times psi theta. So actually, this is the direction of mu. This is the direction of mu. And if you consider mu cross B, mu cross onto this side, and then cross to B. So mu cross B, the top is pointing into the page. So in this case, it is rotating clockwise. So you can consider the torque. The torque is pointing into the page. Okay, so here we have this expression. The torque is mu cross B. Yeah. Actually, we have seen this equation for the electric field. So at that time, the torque is the electric dipole moment cross the E field, and the potential and the energy, and the potential energy here is somehow like negative mu dot B. At that time, negative mu dot E, negative mu dot E. So we just need to change B to E, then we get the same expression. So at that time, we call that one electric dipole moment. And correspondingly, we have a magnetic dipole moment. So the equation will look so similar only by changing E to B, or changing E to B, or changing epsilon naught to 1 over mu naught. Usually like that. Yeah, so similar equation there. Yeah. Okay, so let me finish this one. Yeah, so here we have a circular coil with 250 turns, the area A, and then the current. So the coil is at rest in a uniform magnetic field B, and then with its magnetic dipole moment initially aligned with B. So in the figure, what is the direction of the current of the coil? So in this case, the current should be something like this, because the mu point to the right side. So the I should be somehow like that. So if you see this one pointing to the pointing downward for the face closing to us, and then pointing upward, and then for the face inside, something like this. Okay. So this is simple. So for the second one, how much work would the torque applied by the external agent have to do on the coil, rotating it 90 degrees from the initial orientation, so that mu is perpendicular to B? So for this one, we don't have any potential energy. So if we want to rotate it into 90 degrees to the B field, so what work we need to do? So WA is u 90 degree minus u of 0 degree. So which is nothing but negative mu b times cosine of 90 degree minus negative mu b cosine of 0 degree. And as you know, cosine of 90 degree is 0. This is 0. This is 1. Cosine of 0 degree is 1. So we only have mu b here, which is NIAB. So N is 250 turns, and then I is where? I is this one, 100 times 10 to the minus 6, and then A is this one, 2.52 times 10 to negative 4, and then times B is this one, 0.85. So this is 5.36 mil joule. Okay, so I think that's all for this chapter, and I'll see you this Thursday.